The National Academy of Sciences put together a report that said this is not going to be a problem for just those communities, but it has every risk of becoming a public health epidemic that will sweep the nation and the world. And the US government has to do a whole list of things. It has to protect the blood supply by screening for this HIV virus. It has to stop the spread of the disease by doing a needle sharing program, by putting out information about how the disease is spread, and it has to immediately embark on finding a cure for the disease. Not always has science evidence been followed, however. Some counterexamples are during the Spanish flu epidemic in World War I. The US government came to the Academy and asked for their advice of how to deal with this epidemic of flu that was going through the military. The Academy recommended changing the proximity with which troops were being barracked in order to stop the spread of the disease. The Army said, "We're the Army. We put our troops in barracks. That's what we do." And in the end, more troops died from the flu than from enemy fire. Another example is just recently in 2016, we put a report out on the economic and fiscal impacts of immigration. That report also hasn't been used to guide the nation's current immigration policy. So, as I say, science can inform many critical issues, from feeding a population of 9 billion to dealing with natural disasters to our energy future. However, this will only happen if our nation's leaders and the public in general trust science. So there are many issues, though, that can impact the trust in science. Two that we've heard about today are misconduct and irreproducibility. Now, the globe on the left is from a three-dimensional world map of scientific misconduct in 180 countries. It's very difficult to look at the change in misconduct as a function of time. And the reason I argue that is that with the increase in the movement to make data, methods, materials more open and available, and the encouragement of authors to be more transparent, it's been easier to go back and look at when people have falsified their findings, and also growth of sites like PubPeer have also meant that the community is much more alert to looking for misconduct. The ability of people, because papers are online, to scan images and look for evidence of manipulation of data. All of this means that we have more tools at our disposal to look for misconduct than we could in the past. So I don't think it's possible to do a meaningful comparison with time. But this paper was interesting because it did a spatial comparison. And they normalized it by the number of papers coming out of various countries. And the conclusion of this paper was that in those countries where the scientific enterprise is growing most rapidly, the rate of misconduct is the highest. When we talk about trust, we too glibly don't define when we say, does the public trust science, we don't talk about what part of science we're talking about. Because there's the scientific method, there are scientific studies, and there's the scientific consensus. And those are three different elements of science, all of which are differently deserving of the public trust. So let's talk about the scientific method, which I call the base of everything. The scientific method is what Brian talked about first in the panel this morning, where you come up with a hypothesis, you come up with a method to test it, you gather data, you analyze the data, you say whether it supports your hypothesis or not, you present your findings to others, you let them test it. That's the time-honored scientific method. Anyone can be a scientist if they sign on to using that method. We should all trust in the scientific method. And that is the bedrock, and that is, from time immemorial, the way that we have benefited from science and that society has benefited from science. We should trust in the scientific method, and that should not be necessarily, it should be, we're always, refining it for different fields, but that basically should be something that we trust. Then, at the very top here is the scientific consensus, which is based on all sorts of individual studies. Individual studies support a scientific consensus.
How we choose what to believe is a little more rigorous. It's a little more important. So the question becomes, which evaluations should we believe? So I want to talk to you about two properties that an evaluation can have, right? So one property is credibility. And what do I mean by credibility? It's the quality of being believable or trustworthy. That is, it has some attribute that distinguishes it from all the noise to make you want to believe it. And we'll talk in a moment about what kinds of science today have this attribute. Now, I want to distinguish it from another attribute that is also important to think about if you're a scientist, and that's legitimacy. Okay? And by legitimacy, I mean it's in accordance with a recognized or accepted standard or principle. Legitimacy really matters because it allows us to disagree. That is, we may come to a different conclusion, but if I see how you came to it, I might be able to say, okay, someone who started from where you were and took the steps you took would get to that point. I started somewhere else and took these steps. We can have, if we see each other's arguments as legitimate, we can collaborate and have really interesting conversations because we can pinpoint where we disagree.
Science has clearly been a success story. There's no doubt about that. I think that science has been the best thing that has happened to Homo sapiens sapiens, and in terms of the impact it has had in our lives. It's beyond any question that it has been tremendous. We have many hallmarks of that success. We have 180 million documents that have been published. We have more than 9,000 authors who publish a paper every 5 days. We analyzed all 20 million authors who have published a single scientific paper in Nature a few weeks ago. Some have amazing productivity. We have lots of success stories in terms of major awards, more than 700 Nobel Prizes given in medicine or physics, chemistry, and economics. We have more than $2 trillion invested in research and development around the world every year, with hopefully still some growth, but also some tension about even these funds not being sufficient to really sustain the explosively growing enterprise of science. At the same time, we have some signals that some of that success is just too much. And maybe not all of that is genuine and true. A couple of years ago, we analyzed the entire PubMed worth of data. And from 1990 until 2015, we're talking about 15 million papers. Whenever there was a p-value, 96% of the time, these papers, in the abstract and also in the full text, in about 1 million full text articles that we could download, they had statistically significant results. And practically, they almost always said that this is novel